Hello everyone. So this is a sample problem on how to compute for the pH of the final solution when we mix an acid and a base. So what we have here is, given the concentration of a base, a particular volume of it is mixed with an acid, a particular volume of an acid, and the concentration of the acid is also given. Let's start off by treating the two as a separate, the two system, the acid and the base, as existing in a separate container. So that means we write here, let's say the base is in this container and the acid is here. So the volume of the base is 4 ml. Okay, so don't mind the drawing. Also, we can express this in terms of liters, so that is 0.004 liters. This is going to be relevant in our computation later. Now, the concentration of the sodium hydroxide base is 3 molarity. Take note that the units for molarity is mole per liter. This is also important for our computation later. Now, okay, base, acid. The volume of the acid is 15 ml, which when converted into liters is 0.015 liters. The concentration of this acid is 0.75. These two will be mixed in order for the acid-base reaction to occur. So let's say they're going to be placed in this container. Okay, so we'll place them here, let the acid-base reaction to occur, and then as a result of that, maybe a small amount of the base or maybe the small amount of acid remains, and that will affect the pH of the final mixture. So it depends which one will be left. If base is left, if sodium hydroxide is left, then that will make the pH higher. If hydrochloric acid is left in the solution, then the pH is going to be lower, because that is the effect of an acid to the solution. Okay, so when we mix the two, they will occupy a new volume, and that new volume is going to be the sum of these two, which is 19 milliliters. And in terms of liters, it's 0.019. Okay. Now, when they're placed here, although a reaction immediately occurs, it is best to treat this problem as a step-by-step process, wherein we mix them. They now have a new concentration, because when you mix them, the breakdown of the units for molarity, they will now occupy a new volume. So they will have a new concentration here in terms of molarity. So that's what we need to find out first. Okay, so we will treat this as a step-by-step process, wherein you place it here, they now occupy a new volume, they now have a new concentration, and then after knowing the new concentration, we will deal with the reaction summary. So what is the initial amount of sodium hydroxide? The unit for amount that we are concerned with here is the moles. So to obtain the moles of the sodium hydroxide here at the initial container, we just multiply the volume with the molarity. This volume, this molarity. And we need consistent units, so we will be using the volume in liters. Oops. The amount of sodium hydroxide involved in this reaction is 0.012. Now the new concentration is, we will be using, let's say, M NaOH. This amount placed in a new container with a solution that has a volume of 0.019 liters. So now it's gonna have a new volume. This is the same process that we're going to do for the hydrochloric acid. This is the amount of the hydrochloric acid at its initial container, and then when placed in the new container, this is the new concentration. Of course, we use the new volume. There. Okay. So after mixing the two, the concentrations are these are the values that we will be using for our reaction summary. But first we need to know the chemical reaction equation for this acid-base reaction, and that's going to be an acid reacting with a base produces a salt and water. And we're going to use the next page to continue the computation. This is the reaction summary. So initially we have a particular concentration of the acid and the base. So that initial amount is going to be the amount once they are, the concentration once they're placed in the third container. So for HCl is going to be 0.592. For your NaOH is 0.632. So after that, they will react with each other. Okay, so by the way, there's zero there's zero concentration of the salt NaCl. And then for the water, since this is an aqueous solution, definitely there's a large amount of water, but usually we leave this blank. So here you notice that the concentration of the acid is lower compared to the base, so that means all of it will react, and a certain amount of base will remain. So that means we expect that the final solution is going to be basic. It's going to have a higher pH than 7. So here, all of the acid will be reacted. Point 0.04 mole per liter of NaOH will remain, and then we will have formation of the salt NaCl. And then for water, there will be an added amount of water, but for the final value, we will not place it here. So for the salt is NaCl. It is a strong electrolyte, so immediately this value will dissociate to produce the constituent ions. Okay, so I'm just placing it here because we need to be, sometimes there are problems wherein you're asked what are the concentrations of the species after the reaction. So here you have 0.592 of the chloride ion, but for the sodium ion it's not final because we still have NaOH that will dissociate and release sodium ion in the solution, as well as hydroxide ion. So here we have 0.04. So initial, and then the change is going to be all of it dissociated because sodium hydroxide is a strong base, and the sodium hydroxide will add 0.04 mole per liters of the sodium ion. Also take note that we can bring the value here. Okay. For hydroxide, keep in mind that there is a particular existing amount of hydroxide initially, but the value is very small. The value is this is the value for a neutral solution. Usually to simplify the computation, usually 0 is placed here because this value is very small, that when we compute for the pH, the 0.04 is more relevant than let's say 0.04, 1, 2, 3, 4, 5. Where do we place the 1? Somewhere here. So usually this is just treated as 0. But the reason why I'm saying this is because there will be some very hard computation wherein you have to probably consider this amount. So by the way, for the final values, all of the sodium hydroxide will produce its constituent ions. And then here we have 0.04. And here we have 0.04 mole per liters of the hydroxide ion that will affect the pH of the final solution. Okay, so now what is the formula for pH? Now that we have the most important data, pH is the negative logarithm of the concentration of the hydroxide ion. And what we have here, the pH is the negative log of the concentration of the hydrogen ion, but what we have here is the hydroxide ion. So from here we can compute the concentration of the hydrogen ion using this equation. This is the dissociation constant for water. Okay, dissociation, what do you call this? dissociation constant for water. You multiply the concentration of the hydrogen ion times the hydroxide ion. The value is 1.0 times 10 raised to negative 14, which is true. Okay, as far as I remember, this value is true for, I think it's 25 degrees Celsius or probably 20 degrees Celsius, but this is mostly used assuming in our computation that it's always 25 degrees Celsius. So just keep in mind that this value changes depending on the temperature of the solution. So here we will assume 25 degrees Celsius. Okay, so we will be using the value of the hydroxide, the molarity of the hydroxide ion, which is 0.04. Then we can determine the concentration of the hydrogen ion. There you go. So that is the amount that we will be plugging in here to get the value of the pH. Remember that it is base 10. Okay, so the pH that I obtained is 12.6. So there you go. So other information that are usually relevant is the, let's say, the final concentration of the sodium. This is the final concentration of the hydroxide ion, final concentration of the hydrogen ion. What else? Final concentration of the chloride ion. So HCl, HCl, NaOH. So there you go. So I hope you learned something in this video. Please subscribe to my channel and like this video if it helped you. Thank you very much. See you again for the next video. Bye bye.